Hi, welcome to Pathways to Chemistry. This is Dr. O'Connor. Here we're told to calculate the equilibrium concentration of hydrogen iodine and hydrogen iodide if 0.01246 moles of hydrogen, 0.00828 moles of iodine, and 0.0848 moles of hydrogen iodide are mixed in a 2-liter container. Here we're given K at 703 Kelvin. So the first thing we need to do is determine the molarity of all 3 species. So let's see, for hydrogen gas, that's going to be 0.01246 divided by 2 liters. That gives us 0.00623 molar. Okay, so let's do the same thing for iodine. My pen is going a little crazy on me here. So here's for iodine, and we have 0.00828 moles over 2 liters. And that's going to give me 0.00414 molar. And then of course the same for our hydrogen iodide, and that will give us, let's see, we have 0.0848 moles over 2 liters, and that is going to give us 0.0424 molar. Great. So let's set up our usual concentration table. We have initial, change, and equilibrium. So let's put these initial concentrations in here. So for hydrogen we have 0.00623 molar. Iodine is 0.00414 molar. And for hydrogen iodide, we have 0.0424 molar. Now, we have to figure out what's going on here as far as the change goes. Well, we're given initial concentrations here. We don't know if this reaction is at equilibrium. And so we don't know whether the concentrations of the reactants are going to decrease or increase. The same with the product. So what we need to do is use the reaction quotient, Q, to determine in which way the system will need to proceed to reach equilibrium. So let's go ahead and do that. So what we have is, let's do our reaction quotient here. So we're going to have concentration of hydrogen iodide squared concentration of hydrogen and iodine in the denominator. So let's see, we have 0.0424, we square that, and then divided by 0.00623 and 0.00414. So when we calculate this, we get 69.7. That is Q. So let's compare Q with K. So K is 54.3. In this case here, our Q is greater than the equilibrium constant. So the system is going to have to proceed left in order to reach equilibrium. So it's going to go towards reactants. Now, there are 2 ways we can do this. One way would be to reverse the equation and then go ahead and set up our equilibrium concentration table and determine the equilibrium concentrations. Remember, if we reverse the equation, we also have to take the reciprocal of K. I'm just going to go ahead and leave this as is. I'm too lazy to set up another equilibrium table. So here's what's going to happen then. Because the reaction goes to the left towards reactants. In this case here, the hydrogen and the iodine concentration are going to increase by some concentration X, and the hydrogen iodide concentration is going to decrease by some amount 2X. So at equilibrium, we'll have the following: plus X. Here we have 0.00414 plus X, and then here 0.0424 minus 2X. So let's go ahead then and set up our equilibrium expression here. So we have Kc, and we're going to have the concentration of the hydrogen iodide, okay, at equilibrium, and then we'll divide that by the concentrations of the hydrogen and the iodine. I can see already that this equation is going to be a little messy as far as the calculation, and this is equal to 54.3. Now, if you've watched some of my previous videos, we were able to simplify our expression by making several assumptions. Guess what? We can't do that here. Why? Because our equilibrium constant is 54.3. It's too large. There is no way that we can make the same assumptions as we did before. All we can do here then is solve this for X. I'm not going to go into all the steps of solving, but anyway, what you want to do is collect all your terms, and what you would end up with is a quadratic equation, 50.3 x squared plus 0.35 x minus 4 times 10 to the negative 4. And so we can set that equal to 0. So what we have is a quadratic. Remember, ax squared plus bx plus c equals 0. So we can use our quadratic formula here. So let's see what we have here. Remember, x is going to be equal to a negative b plus or minus the square root of b squared minus 4ac, and that whole thing is over 2a. So what we need to do then is use that quadratic formula. So we know that a is 50.3, b is 0.735, and c is 4 times 10 to the negative 4. So let's go ahead and get this in here. And what we have is x is equal to negative b, negative 0.735. Okay, and that's going to be plus or minus. I hope I don't run out of room here. And I'll just put this like so. And we have b squared, 0.735 squared, minus 4ac. So minus 4 times a, which is 50.3, times c, which is 4.0 times 10 to the negative 4. Let's not forget, this is all over 2a, so 2 times 50.3. Okay, we go ahead and calculate this. We're going to end up with 2 roots, of course. We're going to have x is equal to 5.25 times 10 to the negative 4, or x is equal to a negative 0.0151. Looking back at our table, we see the equilibrium concentrations of hydrogen and iodine, for example. So what you want to do is plug both x's in. Well, first I'm going to plug in the negative x. And notice here, if I plug in a negative 0.0151, I'm going to get a negative concentration. That does not make sense. So there's only one possible value of x, and that is 5.25 times 10 to the negative 4 molar. Now, let's go ahead and calculate our equilibrium concentrations. So here we have them. We have the equilibrium concentration of hydrogen iodide. We have 0.0424 minus 2x, so minus 2 times 5.25 times 10 to the negative 4, and that gives us 0.0414 molar. The equilibrium concentration of hydrogen would be 0.00623 plus x. That's from our table. X is 5.25 times 10 to the negative 4 molar, so our concentration is 0.00676 molar. And then finally the same for the iodine concentration at equilibrium. And that's 0.00414 plus x, 5.25 times 10 to the negative 4 molar. And that gives us an equilibrium concentration of 0.00467 molar. So we have all three equilibrium concentrations. The two major points here, number one, we were given concentrations of all three species. So we needed to calculate Q and compare that to K to determine whether or not the reaction proceeds left or right to establish equilibrium. And second, we were not able to make any simplifying assumptions because K was just very large. So we needed to solve the quadratic formula.